So in this class, we'll discuss 101 sequence detector using Moore Finite State Machine. In our previous class, we have seen Mealy Finite State Machine. And what was the difference between Mealy and Moore? So if you remember, Mealy depends on the output of a Mealy machine depends on the input as well as the previous states. But for Moore type of finite state machines, the output only depends on the previous state. So just a quick recap. This is a state diagram of a 101 sequence detector using Mealy, and we are considering the non-overlapping case. So we'll see how we do it for the Moore type of finite state machine. So what is the target? Our aim is to detect 101 sequence detector. What does it mean? It means you are getting random sequence of bits 1101 101. So as soon as we observe 101, we should take some action, or we should uh, raise a flag. This type of action we should take. So there are two cases possible. First, non-overlapping, and second, overlapping. By non-overlapping, I mean if I observe 101 first time, then this bit sequence will not make any effect on the future detections. It means 101 detected, we ignore, we forget about the previous bits, and now we start observing the next bits from the scratch. There is no effect of previous detection. But for the overlap case 10101, for example, we detect this. So firstly we have detected 101, and this 1 will also act as a input for the next detection. So this is called overlap. So here we have detected 101, and next we will detect 101. So the previous detected sequence also act as an input to the next detection. So this is what we call with this is what we mean by the with overlap case. First, let's start designing the state diagram or the transition diagram for non-overlapping 101 sequence detector using Moore type of finite state machine. So for this, let us assume that we are in initial state of S naught, reset state. So S naught, we are in S naught state, and we are waiting for the sequence 101, right? Because our aim is to detect 101 sequence. So we are waiting for 101 to occur. So this is the initial state or reset state. We are waiting for 101 to occur. If 0 comes, our wait is still that we are still waiting for 101, right? So if we are in state 0 and 0 occurs, we remain in the same state. But if 1 occurs, first step of our wait is complete, as we are waiting for 101. So our first step is complete, 1 has arrived, so we will move to the next state. We'll move toward next state, and we represent it using S1. Now at S1, now we are waiting for 01 state. We are waiting for 01 state. So if we are in S1, we are waiting for 01 state. If 1 comes, our wait is still that we have received. If after 1 we again receive 1, it is again like that we are waiting for 01. So we will remain in the S1. But if 0 comes, we will move towards the next stage. Now we have received 1 and 0, and again if 1 comes, because if we are in states, we have received 1 0, and we are waiting for 1. So if 1 comes, we move towards the next state, and we raise the flag. Since our 101 has appeared, or occurred. So we should make the output as 1. Since it's a Moore type machine, we are not using that slash. Right? For melee, we write what is the corresponding output for each input. But for Moore machine, the output only depend on the state. So for all other states, the output will be 0. But as soon as we arrive at S3 state, so our wait is complete 101. So we will raise our flag and we'll make the output as 1. What happens? So we have to complete this this diagram here. What if we are in S2 and 0 arrives? We are in 1, we have received 1 0. So we are in S2, we are waiting for 1. But what happens if 0 arrives? If 0 arrives, we have to again wait for 101. So if 0 arrives, we have to wait for, we have to wait for 101 again. So we will move towards S0 state. So S0 is waiting for 101, waiting for 101. Here we are at S1, we are waiting for 01. Here we are waiting for 1. But if 0 arrives, we will go back to our S0 state and we will start waiting for 101. So from each state, we need to see all the two possibilities. We are in S2, 0 arrives, we move here, 1 arrives, we move here. We are in S1, 0 arrives, we move here, 1 arrives, we move here. But what happens if we are in S3 state and 0 arrives? So we have received 101 and we encounter a 0. Then we have to move to S0 state and we have to again start searching for 101, or we have to wait for 101. And we are in S3 and 1 arrives. It means 1 has arrived, so we will move towards S1. 1 has arrived, since 101, 1 arrived, so we have to wait for 01. So we wait for 01 means we have to reach transit to the S1 state. Since there is no overlapping allowed, we are not considering the previous one as a input to the next detection. So just this is a difference. So this is a transition diagram for the non-overlapping case. How would you make the state diagram for the transition case? So just try to draw the state diagram for transition state. The only difference is this one will be considered as the input to the next detection. So let's make the uh, state diagram for the overlap case here. Please try it. 101 detection with overlap. So let's try to make the state diagram for this. We are considering the two cases in parallel, and then we will only discuss how to proceed further for this case, and we will assume that if you know how to solve a state diagram, you can also solve with overlap case. So just we will draw the state diagram for with overlap, and then we'll move towards the next step for the without overlap or non-overlapping case. So state diagram for overlap batao. We are in S naught state, so we are waiting for 101. There is no flag, and since it's a Moore type of design, Moore finite state machine, the output only depends on the in state. So we will write output like this. So we are at S naught, we are waiting for 101 to happen. If 1 happens, then we will move towards next state, and then 0 happens, we will move towards next stage, And then if 1 occurs again, we will move towards S3 and we will make it. We will raise the flag. Now we'll complete the rest possibilities. If we are in S0, 0 arrives, we have to still wait for 101, waiting for 101. Here we are waiting for 01, here waiting for 1. We are waiting for, we have uh, received 1 and we are waiting for 01. And what happens if 1 arrives? It will work as only 1 has arrived. So we are still waiting for 01. Next, we are in S2. We have received 10 and 0 comes. So we have received 10 and 0 arrives. So it is like we have to again wait for 101. Next, we are in state 3. It means we have received 101. There are two possibilities. Either we are in S3 state, 0 or 1. So if 0 arrives, it means since overlapping is allowed, you need to see that you are in S3 state and 0 arrives. It means you have received 10 and you are waiting for 1. So if you are in S3, 0 arrives, it is equivalent that overlapping is allowed that you have received 10 and you are waiting for 1. Right? Next, if you are in state S3 and 1 arrives, it means you have received 1011. So you have received 1 single 1, and you are waiting for 01. So this is the state diagram corresponding to the not corresponding to the overlapping case. So this is the minute difference. If you can see, there is only I think two, this one and this one. So yes, only one difference. This for overlapping case, this is the state diagram, and for non-overlapping case, this is the state diagram. So if you have any doubt, you can ask till now. Otherwise, we will move forward. Okay, so I assume you don't have any doubt. So let's solve this finite state machine. This is the state diagram, right? Then the next step is to write the state table. So mm I have to again draw this. Otherwise, okay. So just try to write this state table, and I will just write this state table here. State. So first step is complete. Then we will write state table. We'll consider non-overlapping case, and I assume that if you know how to solve non-overlapping case, you can also solve the overlapping case. So non-overlapping case state table is, we have to write what is the state table, what is the previous state, and if the input, there are two possibilities, you are in some state, either of the input can arrive, input 0 or 1. So what will be your next state, and similarly the output. But the difference in Moore machine is that the output is independent of the input. So we don't have to write outputs for the both of the possible inputs. We have to write all output depending upon the state only. So we will not write the two columns for the output, what we did for the Mealy. So this is the difference in state tables of Moore and Mealy type of FSM finite state machines. So there are four states, right? S0, S1, S2, S3. So please write, if you are in S0, S1, S2, S3, outputs are very simple to write because output only depends on the state you are in, correct? So if you are in S0 state, output is 0, sorry, S0 output is 0, S1 0, S2 0, S3 1. So if you are in S3, output is 1, correct. So if you are in S0 state and if you just observe the state diagram, please complete this state table. I would write it here, and please check and stop me if I make any mistake. Please take 2-3 minutes and try to fill this. Our present state is S naught. Input 0 arrives, we still remain S naught. Input 1 arrives, we move towards S1. We are in S1. If input 0 arrives, since our aim is to get 101, we move towards S2. And if 1 arrives, we remain in S1. If we are in S2, if 1 arrives, we move to S3. And if 0 arrives, we move towards S naught. We are in S3. If 0 arrives, we are in S3. If 0 arrives, we move towards S naught. And if 1 arrives, we move towards S1. So, yes, the state table is right. So, this is the state table. Next it, we have to assign some binary number or binary code to each state. Correct? So, one simple assignment, I told you that there can be various assignments possible. But one simple assignment, first you have to also check the whether there are some redundancy. As I can see, there are no redundancy. How would you check the redundancy? If the last three columns for some rows is same, we will say that these two states are redundant. So what we saw in melee type of design, that these two states were, we have seen that since these two rows were same, so we said that S0 and S3 states are in fact redundant, are actually same. So we can replace S3 with S0, but here we don't see any redundancy, that no three columns of any row is same. So we can move forward. There is no state reduction possible. So next is state assignment. So state reduction, we have created a state table, designed state diagram. From the state diagram, we have achieved or derived the state table. And since there is no reduction, then we do state reduction. But there is no state reduction here. So we will do the assignment, the code assignment to each state. So we'll make a simple assignment. S0 is 0, 0, S1 is 0, 1, S2 is 1, 0, and S3 is 1, 1. So we will just write 1, 2, 3, 4. We'll assign the number. So we have to replace S0 with 0, 0, S1 with 0, 1, S2 with 1, 0, S1 with 0, 1, S0 with 0, 0, S3 with 1, 1, S0 with 0, 0, S1 with 0. So this is the states. Now we have assigned the binary values or the binary code to each state. So what is the meaning of why we assigning the values, these binary values to each state? Because what is the meaning of state? There are four states here, right? So four states can be represented by using two flip-flops, right? So there are four different states. So if you have a two flip-flop, output of each flip-flop would give you a state of, so if there are two flip-flops, there are four possibilities, 0, 0, 0, 1, 1, 0, 1, 1. And accordingly, you can say that we are in which state. Okay. So this 0, 0, 0, 1 is now, we have said that this is the output of the Fth flip-flop, and this is the output of the Bth flip-flop. And what type of flip-flop is there? We will discuss it later, but we'll say that this is the next output of the Ath flip-flop, and this is the next output of the Bth flip-flop. Since each of this binary, left or right, will represent one flip-flop. So each state S0 is, so there are two flip-flops we have to take in order to represent four different states. So we'll say if our both the flip-flops are in 0 output, then they are in S0 state. So this is how we are representing these S0, S1, S2, S3 using flip-flop. So this is flip-flop A, this is flip-flop B. Now since we are designing sequential circuits, we have to find out how to provide the input to these flip-flops, correct? And what type of combinational circuit will give you the output. This is what we have discussed in the initial lecture, that we have to design the combinational circuit which will give input to these flip-flops, and will also design a combinational circuit which will give you the output. Okay, and so we have QA, QB, QA plus QB plus QA plus QB plus. So this is the output of the flip-flop at the next clock cycle, right? So next we would ask, we have the present state, we know what next state we want. Next we have to ask which flip-flop you want to use in order to represent these transitions. So many possibilities are possible, D, J, K. So we will say that okay, we want, let's take D flip-flop. So code assignment ho gaya, we have done the code assignment. Now we have to ask which flip-flop. So we want that we need to implement, or we need to get this state table using D flip-flop. So which excitation, I mean, how we are getting the excitations. These are the excitations that we are in QA QB and we are moving towards QA QB plus. So if you remember excitation table of D flip-flop, we can easily solve this problem. So let's make it again. So we are in QA QB, QA plus QB plus, given input is 0, input is equal to 1. What is the next state of our two flip-flops? The output. I have to write it a bit small. So this is QA QB, QA plus QB plus, QA plus QB plus, given input is 0, input is 1, and output. So DA and DB. So we'll complete 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1 0 0 1 0 0 0 0 0 0 1 0 1 1 1 0 1 0 0 0 1 0 0. So if you just observe here, input is equal to 0, dB, input is equal to 1, dB. So first see this, when you are in QA state, your flip-flop A is in QA state and input 0 arrives, input 0 is there. What type of what type of DA input will provide you 0? So if you remember, whatever is the input at DA, the same will appear at the output at the next clock. QA plus means next state means what happens at the next clock. So this flip-flop A, the output is 0. How will you get the output 0 at the next clock? If you provide input 0. At the D, if you provide 0, you will get 0 here. Next, similar thing we can use here, that if you want at the next clock 1, we should provide 1 at DA, 0 0, and you can just fill the. For D, it is simple, and similarly you can write the DA value for the input is equal to 1 case, 0 0 1 0 1 1 1 0. Next step is find out what is the, as I said, we have to find out what should be the value of DA in terms of QA, QB, and the input. Because if you remember for the definition of, or when we discussed the sequential circuits are memory elements, and we design a combinational circuit in order to feed the memory element which will decide the next state of that memory element, and the combinational circuit, the input is previous state as well as the input. Correct? So previous state and input, you have to find out how this will affect what should be the this function, right? This we have to get the previous state, QA, QB, and the input. For DA, similarly for DB, we have to find. So for this, the best way is to form a K-map. So design K-map for DA. Design K-map for DA. Design K-map for DA. So here I will write QA, QB. Here I will write input. So input 0, input 1. QA, QB can be 0, 0, 0, 1, 1, 0, 1, 1. So what is the value of DA when your QA, QB is 0, 0 and input is 0? 0. So just fill it here. Similarly, 0, 1, input 0, 1, 0, 0. So it is simple. Here, what is the value of DA? This you have to see. When input is 1 and QA, QB is 0, 0, 0. So you have to write this column 0, 0, 1, 0. And next, we have to reduce it. So DA is QA bar, QB, input bar, plus QA, QB bar, input. So this is how we should choose DA. Next, similarly, design K-map for DB. For DB. So I would just post this video, stop the video at your convenience, solve the problem, compare your results. 1, 0, 1, 1, input is 0, output is 1. So 0, all zeros, and 1, 1, 1, zeros. So all zeros. I'm just seeing what is the value of DB when QA, QB is 0, 0 and input is 0. So this 0, 0, 0, and here 1, 1, 1, 1, 0. 1, 1, 1, 0. So next we have to further reduce it. I think I make a mistake. It's all 1. So I should also write 1 here. Sorry. Because at input 1, QB plus is 1, 1, 1, 1. So we should provide QB DB as 1, 1, 1, 1. So here I should write 1. So if you reduce it, you can take this. So DB is input. Next, we have to write K-map for output. Since if you remember, what is the meaning of designing a sequential circuit? You have to find out what is the combinational circuit for output as well as combinational circuit for the input of this memory elements. So we have completed the first step. We have found out the combinational circuit for the memory elements, this DA and DB. And next we have to find out the combinational circuit required for the output. And as we are designing Moore machine, the output will only depend on the state. It will not depend on the input. So we have to draw output K-map for output only as a function of QA and QB. Correct. So by simply observing also you can write that output should be QA, QB, right? There is no need to draw K-map also. So output is QA, QB. Output is also because we have to find out the output as a function of QA and QB only. Since it's a Moore machine, the output does not depend on the input. So we have to just write output as a function of QA/QB. For this, you have to do this. Output is QA/QB. Next it, how will you design the circuit? So circuit diagram. This is your 2D flip-flops. This is DA. This is your DB. This is QA, QB. Here we are getting the sequence, arbitrary sequence 1 0 0 0 0 1 1 0. So this is the input, and you have to provide QA bar QB, QA bar. So QA bar, we have to design a AND gate where this is QA bar, this is QB, and input bar. Here you have to write input bar. This along with QA QB bar input, QA QB bar. This is QB bar. This is QA, and input we have to we have to perform an OR operation, and next we have to provide DA as input. So this is the combinatorial circuit for DA. Similarly for DB, it is only input. You have to only provide input to DB. Clock will be there. So clock is there. QB and QB bar. So this Q and QB will come out from here. So just I'm doing it for neat because for the reason of neat. I mean it looks fine, right? It looks good. Next is how would you write the output? The output is QA QB. So here QA QB. So we have to connect QB and QA. So this circuit, if you implement this circuit and you provide arbitrary sequence here, whenever 101 is received, this output will become 1. So if you put a LED here, you will see that it will glow whenever it will see 101 sequence. So this is comparatively easy if you do it using D flip-flops. So if somebody asks you to perform the same operation using JK flip-flop, how would you do that? Or T flip-flop? So at this step you have to write. So, okay, I will first summarize what we have done till now. कोई doubt है तो पूछो एक बार. If you have any doubt, please ask. What we have done? Can you please summarize? Or someone whose microphone is working, please summarize. Anyone? Jaldi karo, we'll finish fast. We have designed 101 sequence detector using Moore machine, right? Moore Finite State Machine. Please somebody, can you hear me? I think. Okay, let's do it using JK flip-flop. So for this, up to this state that we have obtained state table and we have assigned the values to each state. Up to this state, the things will be common. So QA, QB, QA plus, QB plus, input equal to 0, input equal to 1, QA plus, QB plus, and the output. Next, we have to see when your input is 0, input is 0, and you are now using JK flip-flop, right? So we are now using JK flip flop. JA, KA, JB, K, and the outputs are. Now we have to find out the combinational circuit here. How should we get JA for this, JB for this, and the output, right? So when our input is 0, we know the excitation that we should move from QA to QA plus. So what type of JAKA will give you this JB KB? So we move towards QA to QA plus. So we have to see that JAK requirement. How what JAK would you move from QA to QA plus? So first we have to fill this 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 0 0 1 0 0 0 0 0 0 0 1 0 0 0 0 1 0 0 0 1 0 0 1 0 1 1 1 0 1. So here we have to write 0 1 0 1 1 1 0. Input is 0. We are moving towards QA to QA plus. So what type of JK combination will give you this? So if you see that we are in from 0, we are in 0 and the next is also 0. So either we reset it, either we reset this flip flop, either we reset this flip flop, or we don't make any change. The hold, right? So there are at if we are in hold or we reset. So if you remember, what type of combination will give you this? So you can use JK as 0 0 or 0 1, right? So these two combination of JK will provide you this type of excited. Otherwise, you can do one thing. You can write the excitation table for JK flip flop, and by observing the excitation table, you can easily fill this. So the excitation is from QA to QA plus. We are moving from 0 to 0. If you just observe the excitation table of JK, you will get this 0 cross. So if QA is 0, QA plus is 1, QA plus is 1. So what type of excitation is needed? Whether we are toggling or we are setting. So please check from the excitation table of JK flip flop. We are in 1, 0. So either 1, 1 or 0 1. So cross 1. 1 to 0 means same, right? We are moving from 1 to 0. So same, cross 1. Please just try to fill JB and KB. What should be the value of JB and KB if you move this excitement that you are in QB and you move towards QB plus? So see 0 0 means we have already seen 0 0 means 0 cross. 1 0 1 0 we have seen cross 1. Just draw excitation table of JK here. QA, Q plus. And JK. Just write the excitation table 0 0 0 1 1 0 1 1. For 0 0, this is the excitation table. Just type the excitation table, write the excitation table 1 cross. This is the excitation table of JK. So just fill the excitation table, and from the excitation table, you can easily fill this. So 0 0 means 0 cross, 1 0 means crossing. So similarly, you have to write for input is equal to 1, JA, KA, JB, KB. Means your input is 1, you are in this present state and you move towards this state. So what type of input is required at JK to give you such excitations? Correct. So you have to see you are in 0, you move towards 0. What type of excitation will be needed? 0 cross. You don't care about K, and you are in 0, you move towards 0. What type of excitation? 0 cross. You are in 1, you move towards 1, right? So 1 1 means either hold or set. So cross 0. You are in 1, you move to 0. It means 1 0. I think cross 1. 1 0 means toggle. Toggling is allowed, and resetting, right? So cross 1. Similarly, when input is 1 and what type of value of JB will give you this excitement? 0 to this, 0 to 1, 1 cross. It's always good to write a complete excitation table. It will make job easier. And 1 to 1. 1 to 1 will be like either you are in 0 0 or 1 0, right? So cross 0. So cross 0, cross 0. You are in 0th state and you move towards 1, 1 cross. You are in 1, you move towards 1, 1 1 means cross 0. So now we have the values of JAK, JB, in terms of. So now what you have to do, you have to find out this function, right? Previous state as well as the input JA, what type of function will provide you this excitement? QA, QB, JB, because our aim is to get the combinational circuit, right? Combinational circuit which will give you this excitement. So this you know. So combinational circuit means this function. What I'm saying that this is some combinational circuit of previous state at the input. So F1, QA, QB input and KB, G1, QA, QB and the input. So now your task is to write K map for JA, K map for KA, K map for JB, K map for KB, and you have to find out what is the relation between QA, QB input with J and similarly for J, KA, JB, KB. करो इसको कैसे करोगे? So K map for JA, QA, QB input. Input is 0, input is 1. 0 0 0 1 1 0 1 1. Similarly 0 0 0 1 1 0 1 1. Your input is 0. So you have to copy this column, because what we are doing here, we are writing K map for J as a function of QA, QB and input. QA, QB and input. Input is 0 first. We are taking input as 0. So this is 0 1 cross cross. 0 1 cross cross. And now we have to write K map for J as a function of QA, QB when input is 1. QA, QB when input is, here I should write input is equal to 1. Input is 1. So this X, JA as a function of, sorry, yeah, when input is 1, it was my bad. We do not copy this column. In fact, we have to copy this column, correct? 0 0 cross cross 0 0 cross cross. So next we try to simplify this. So this is the simplification, that we should try to cover 1 with the maximum largest possible square. So this is how we can cover. So JA is equal to this I have, यहाँ पे I have done mistake, 0 0 0 1 1 0 1 1. Here also I did the same mistake, I think, right? What mistake I have done here? 0 0 0 1 1 0 1 1, correct? But in K map it is 0 0 0 1 1 1 1 0. So थोड़ा सा I think we have to correct it. Please correct. Yeah, one mistake is here. Here there is no change because one there is both one, so the thing will be same. But here a bit of change will happen. QA bar, QB, input bar, and no, it's good. The output is same because we are not, actually we are not making group, so the this is okay. The expression is okay, but yeah. So here we need to do this, and we have to swap this. So we have both are cross, so no issue. J is equal to QB input bar. Similarly, you have to write K map for JB, K map for JA, K map for KA, K map for JB, K map for KB, and next you have to write K map for output, but output is only function of QA/QB, and try to solve it, and we'll discuss it in the next class, because I think it's too much for you. Just you need to write the K maps for KA, JB, and KB, and K map for output as a function of QA/QB is simple. So output is QA/QB. You can see output will be QA/QB. For JK, JB, KB, please solve it and write the expression, and we'll see it in the class. So if you have any doubt, you can ask.